So we start with the session number 3 of this conference, and the first talk, I understand, is going to be a video recording.
No, it's just video talk.
Yeah. It's just a video talk, right? Yes, it's a video talk. Is going to be by Bryan Zhu.
Hello, everyone. Yeah, thanks for having us here. It's great to be here. I'm Bryan, and I'm here with Nick, and yeah, we're going to be talking about Meter ML and our work with a multi-sensor Earth observation benchmark for automated methane source mapping. All right, so methane is important because it contributes to over a quarter of present-day global warming. And we have multiple methane measuring satellites, either currently on orbit or launching soon. So this gives us a new opportunity to attribute methane emissions to sources on the ground so that we can either monitor them or regulate them. However, doing this requires a comprehensive map of methane emitting infrastructure on the ground. And the problem is that there are only a few public data sets for this kind of methane infrastructure available today. Much of it is incomplete or erroneous, especially globally. And this is where AI can help. So in the past few years, the combination of better remotely sensed imagery and better computer vision means that it's become possible to develop models that can map this kind of infrastructure at a large scale from aerial imagery. So we've seen some previous work, a number of works mapping particular kinds of infrastructure, such as oil refineries, CAFOs, and wastewater treatment plants. However, all of these AI efforts have needed large labeled data sets, and as I mentioned before, there aren't many publicly available such data sets of high quality. And our work aims to help bridge that gap. So we're working with a recent Stanford-led initiative known as Meter to produce a global public database, and to empower the AI portion of this, we're developing Meter ML, which is a public multi-sensor AI plus remote sensing data set that will hopefully enable the machine learning community to more effectively address this problem of methane mapping. So let's talk about this data set. Our data set consists of 6 different kinds of methane emission sources from across the United States. We focus on CAFOs, landfills, coal mines, natural gas processing plants, oil refineries and terminals, and wastewater treatment plants. In order to find these sources, we combine data from a number of public sources, from government to nonprofit to academic. We filtered these sources to make sure that they were usable. For example, if we actually had the rights to redistribute them, and also to make sure that the facilities are actually visible from aerial imagery. And then we deduplicated them and downloaded them. Because it was possible for multiple types of facilities to be close by in one image, these images ended up being multi-label images. And so our classification task is a multi-label classification task. So those are positive samples. We also collected a number of negative samples, which contained no facilities. And to do this, we defined a number of negative categories, which we've listed here, and used the Descartes Labs geovisual search tool to collect up to 1,000 images per category. We then went through and made sure none of these negatives overlapped with the actual positives in our data set. Once we had all of these locations, we downloaded these images from 3 different remotely sensed image sources, NAPE, Sentinel-1, and Sentinel-2. And so here's an example of what the same location might look like across all of our different bands and different satellite products. For each coordinate in our data set, we used a 720 by 720 meter footprint around that coordinate. So in total, we collected around 86,000 points, with the breakdown across classes shown on the slide here. Then 2 Stanford postdocs with expertise in methane emissions and related infrastructure individually reviewed around 1,500 of these images, which we then split into our validation and test sets, with the remaining images going into our training set. So now I'm going to pass it over to Nick to talk about the experiments that we ran on this data set.
Thank you, Bryan. I'll now be talking about our experiments and key results. So we conduct multi-label classification experiments using a DenseNet 121 architecture that is pre-trained on ImageNet. For a given data point, our model predicts a 1 or a 0 for each methane source category, where 1 and 0 correspond to present and absent respectively. If a model predicts a 0 for all 6 methane source categories, the data point is classified as being a negative. Our first experiment examines the effect of different satellite bands and products on model performance. We use Sentinel-1, Sentinel-2, and NAPE images with a variety of different bands. In terms of the macro average validation AUPRC, NAPE with all bands has the best performance, achieving an AUPRC of 0.548, followed by the combination of Sentinel-1, Sentinel-2, and NAPE. There is a significant drop in performance on all classes when moving from NAPE to Sentinel-2, highlighting the benefit of using high spatial resolution imagery. For NAPE, the inclusion of non-visible bands improved performance for all classes. However, for Sentinel-2, the inclusion of non-visible bands substantially improves performance on mines, but substantially degrades performance on landfills. Our next experiment examines the effect of image footprint and spatial resolution on model performance. Image footprint is defined as the amount of area on the ground that's captured by the image. To investigate the impact of footprint, we center crop the 720 by 720 images to obtain 480 by 480 and 240 by 240 images. This corresponds to a 480 by 480 and 240 by 240 footprint respectively. Note that this reduces the area on the ground with spatial resolution held constant. We then upsample these images back to 720 by 720 to avoid any differences in performance due to varying image size. To investigate the impact of spatial resolution, we use cubic spline interpolation to downsample the 720 by 720 images to 480 by 480, which gives me a 1.5 meter resolution corresponding to Airbus spot imagery, and to 240 by 240, which gives me a 3 meter resolution corresponding to PlanetScope imagery. These images are then upsampled back to 720 by 720 to maintain a constant image size. We find that the largest tested image footprint achieves the highest overall performance, as substantially outperforms smaller footprints across all classes except for wastewater treatment plants. This may be explained by the fact that a large number of smaller wastewater treatment plants are surrounded by industrial buildings and other infrastructure, and such cropping out this infrastructure improves the model's ability to identify the salient features of wastewater treatment plants. We further find that the highest spatial resolution achieves the best overall performance. However, the coarser resolution models follow closely behind. This result suggests that models developed at 1.5 and even 3 meter resolution have the potential to perform almost as well as 1 meter resolution models, which has implications on global applicability, as Airbus Spot and PlanetScope are globally available at 1.5 and 3 meter resolution respectively. For each methane source category, we select the experimental configuration, the product band footprint resolution combination, that achieves the highest validation AUPRC for that class to serve as a class expert for our holdout test set. The per class expert model obtains a macro average AUPRC of 0.558. The model does especially well on K-folds and refineries and terminals, possibly because these sources have very distinctive features. It performs more poorly on the other sources, especially landfills, which do not have clear distinctive features, which do not have many clear distinctive features visible at the 1 meter resolution. The experiment suggests that the choice of product band footprint and resolution can lead to large differences in model performance. This suggests that there is significant room to explore approaches that leverage the multi-sensor, multi-spectral aspects of meter ML. Our experiment models, including Sentinel-1 and Sentinel-2, achieve high performance on identifying K-folds and refineries and terminals. This suggests that there's large potential to map these facilities with NAPE imagery in the US and potentially globally with Sentinel-1 and Sentinel-2. We are very excited to announce that our website for the project has been launched, And the dataset will be made available on this link in the next few days. Finally, we'd like to thank our co-authors who have contributed generous amounts of time and energy into making this dataset and project possible. Thank you. Do you have any questions?
I can ask a question. You showed results from different algorithms and different sensors and their performance, and they seem to differ in their quality of which classes they perform better on. Do you see possibilities of combining them to improve his performance on individual classes instead of using each one of them each at a time, but if you use them collectively? Do you see an opportunity to improve performance?
Oh, do you mean like running all of the models on
Somehow
like this on this task, and then
Yes.
like say like maybe take the whatever class most of the models predicts as?
That will be a simple way to do it, but something along those lines. In the sense that the question is there a complementary information available from these different classifiers that we leverage to improve overall performance? And of course, the simple voting would be one way, but there could be other ways as well.
Yeah, I mean, there are a number of ways that we could approach this. There's a lot of room to explore with this data set. And we did very simple things just as first experiments in this. Like, for example, when we were combining bands and stuff, we just basically concatenated the images by channels across the bands, whereas you could think there are more complex ways to treat like each band separately and then concatenate things later on, so there's or like what you mentioned is like with combining all the different models at different resolutions and footprints and stuff. I think there's a lot of room to explore different approaches with this data set. And yeah.
Thank you. Any other question? All right, well, let's thank the speaker one more time. And the next presentation is also going to be virtual, and I believe it's by Yifan Wang.
Hello, everyone. My name is Yifan Wang from Shenzhen University in China. Though I was unable to attend the conference, but sharing our work in this way is also a group experience. Then I will introduce our work, Centermark's convolutional transformer for hyperspectral image classification. Considering that everyone here are familiar with the hyperspectral image, so I just briefly introduce the background knowledge. The biggest difference between hyperspectral image and RGB image is that the hyperspectral image has spectral information of the land covers, which means we can distinguish the specific material by its corresponding spectral curve. This is exactly what hyperspectral image classification does. It also serves as a supporting technology for the above applications. However, hyperspectral image classification is not a simple job. We visualize the phase color map and spectral curve of the Pavlík University dataset. As shown in the figure, we can see that the spectral curve of the same land covers are different, and the spectral curve of the different kinds of ground objects are similar, such as the bitumen and bricks. This phenomenon widely exists in hyperspectral image, so it's difficult to distinguish the categories of ground objects only by spectral curves. Nowadays, we usually introduce the spatial information around the center pixel to bring more homogeneous pixel and context information into the samples. The model input will be a data cube, and we will still only have the annotation of the center pixel. This change can make the sample easier to identify than before. However, today's mainstream method, the convolutional neural network, is not good at capturing long-distance relationships, which means we will lose some useful information, such as the relation between ground object 1 and ground object 2. That's what the transformer model excels at. If we can reasonably introduce the transformer model, then we can better perceive the relationship between ground objects, but not limited by the size of the convolutional kernel. Spectroformer is one of the earliest transformer-based methods for hyperspectral image classification. In this paper, the same numbers of bands are regarded as a patch. The remaining framework mainly follows the design of vision transformer. The figure on the right is the experiment result on Indian pine dataset. Though the accuracy will increase when we increase the proportion of the training sample, but such a result is not satisfactory for practical application. When we use 10% samples for model training, the classification accuracy is only about 50%. This may be a common problem with the transformer-based model. They are data hungry. However, 10% of training sample contains at least thousands of annotated pixels, and pixel level annotation is time consuming. Therefore, it's not enough to introduce the transformer model and just make it work. We prefer it to perform better under sample limited conditions. Our method attempts to address the problem in two ways. The first one is to design a new embedding module that matches the characteristic of hyperspectral image. Generally speaking, when we don't have enough sample for model training, the linear embedding module should not be the first choice because the performance of the embedding module greatly affects the performance of the model. So we need a lightweight but effective embedding model to replace it. In our method, we choose a 3D convolutional neural network as the embedding module. Its detailed information is listed on the table. Compared to the commonly used linear embedding module, it's very lightweight but powerful. Furthermore, inspired by the design of depth-wise separable convolution, we further separate the sample from spectral dimension in the beginning, and parallel 3D convolution option will perform to each subband to obtain the local spatial spectral embeddings, and then we combine them to get the global embeddings. Finally, the embedding token will be input into two connected transformer encoders and get the classification results. In particular, the convolutional embedding module can be simply implemented by group convolution. If we use 10% sample to train our network on Indian pine dataset, the classification accuracy can be close to 100%, which also proves that a reasonable framework design is very necessary. The second way is to design a self-supervised learning task that can effectively utilize the unlabeled samples. Here is the flow chart of our proposed pre-training task. The encoder composed of our proposed convolutional transformer network, and the decoder composed of two transformer encoder blocks. The idea mainly comes from the mask image model. We realize that if the decoder can reconstruct the center pixels through the information of the rest area, in this process, the output of the encoder will be more relevant to the center pixel. That's what we want. So we just mask the token generated by the center area to make the decoder lose its information and use a learnable vector to replace it. Then through the self-attention module in the decoder, the learnable vector can get more information about the center area from other tokens, and we can take it as the representation of the sample to recover the center pixel. In the pre-training stage, we use 17% sample for model training and 30% sample for evaluation. The evaluation experiment shows that after pre-training, the overall accuracy has been improved by 1.3% and 2.7% on Salinas dataset and YRE dataset, respectively. Here are the comparative experiment results on the Salinas dataset. We use 5 samples per class for model training, and the rest sample are used for evaluation. Our model has obtained obviously of the advantage on 3 evaluation metrics. We also visualize the classification map. It can be seen that our methods successfully restore the distribution of the land covers. The other methods have more noise point and classification errors. The results on YRE dataset are similar. Our model achieved the best results. It's worth mentioning that the YRE dataset is a large scene dataset, so it's hard to give a label to every pixel. Only part of the pixels are annotated. The first row is generated by CNN-based method. We can see that there is smearing in it. And the second line is generated by transformer-based method. And they better restore the base outline of the land covers, which also prove the potential of the transformer model in complex scene classification. In summary, we propose a pre-training task and a convolutional transformer for hyperspectral image classification with limited training samples. For our pre-training task, we hope to improve the convergence speed and generalization ability. For our backbone network, we hope we can introduce multi-scale feature as the embeddings feature. In this way, our model can be adapted to different datasets. Thanks for listening and hope you have a nice day. Thank you.
Thank you for the wonderful talk. So I was curious, I work with multi-channel climate data often, and I was wondering if you think this sort of approach could possibly generalize to other types of spatiotemporal data where we have, other than RGB features, sort of greater feature dimensions in the channel space, and maybe how that would adapt. If you think this approach could work on image types that maybe are more general than hyperspectral imagery, but just sort of other types of imagery with multiple channel dimensions, and maybe how this method could adapt to that type of data.
Yes, I think the transformer model is you can take it as a tool. So it can, if you get the proper way to embed your data. So I think that the transformer can use for every kinds of data. If you get the proper way to get the embedding process.
Okay, yeah, thank you.
Thank you.
I assume your concern was that in hyperspectral data, there's a lot of autocorrelation as you go from band to band, and there's the climate data I'm assuming you're talking about, or like pressure, temperature,
Yeah,
humidity, wind speed.
which sometimes there is correlation between those channels,
But not of the kind that you see in the
Yes,
hyperspectral. So I think the answer is you should try.
Yeah.
And the other that you're not assured of success. You have to try and see what happens, right? That's how I would interpret it. Another question.
Okay, I wonder, have you compared with other transformer-based method, for example, the Swan transformer or some attention-free transformer whose parameter is smaller than your model presented? And the second question is that in your transformer, you just consider the channel of the hyperspectral as the input, and have you considered the spatial feature of the hyperspectral images? Yeah.
Yeah, the first question. First, I don't know there anybody use string transformer to tackle the hyperspectral image classification. But our model is very lightweight. Here, there are some transformer-based model are published, and I can just they are larger than my model. So, and the second question. So when we use the 3D neural network as the embedding model, so the 3D convolutional kernel can get the spatial spectral information at the same time. So our embedding are the spatial spectral embedding, but not only considering the spectral information.
All right. Thank you very much. Let's thank the speaker one more time. And our next presentation is by Yonghao.
So hello everyone, my name is Yonghao. The topic I will share with you is about AI security in remote sensing. Specifically, I will present a task-guided denoising network to conduct adversarial defense for remote sensing scene classification. This is the outline of my talk. I will start with some background knowledge of the adversarial attack and defense. So the main idea of adversarial attack is to generate some specific perturbation. And after we add this kind of perturbation to the original clean image, we can generate the corresponding adversarial example, which can cheat the deep neural network to make a wrong prediction. So based on this technique, we can change the predicted category of an airplane satellite image into the runway category with very high confidence. And also, we can even change the spectral characteristic of different ground objects in the hyperspectral domain. And the technique behind all this interesting application is the adversarial attack algorithm. Here we show one of the most representative algorithm, which is fast gradient sign method, FGSM. So the key idea here is to back propagate the wrong gradients to the input image X so that we can generate the adversarial example. And one limitation of the existing adversarial attack algorithms, like fast gradient sign method, is a dependence of the knowledge of the victim model, so including its architecture and the parameter values, because we need all this information to calculate gradient here. However, in the practical application scenario, it will be very impossible to get all this information. So we are thinking about, can we generate some universal adversarial examples so that we can cheat different neural networks, so that given an unknown victim model, we can also conduct the adversarial attack. To answer this question, in our previous TGIS paper, we proposed the mix-up attack. And the key idea here is to attack the shallow features of a surrogate model using the mix-up samples. And these are some key equations of this method. If you have interest, you can refer to this paper. And now that we can have this kind of universal adversarial examples, a natural question would be, how can we conduct some defense methods to improve the network's resistability? And here we summarize 3 different strategies. The first one is adversarial training, where we will use both the clean image and the corresponding adversarial examples to train a deep neural network. And the second type is to directly use some well-designed architecture to train the deployed models. And third direction is use some transformation-based methods, including like JPEG compression and downsampling or even color jitter. And in this study, we consider adversarial examples as a kind of noisy images, so that we directly do some denoising work as a kind of defense. And based on this idea, we propose the task-guided denoising network. And this is a flowchart of our method. There are 2 main components, including one is the task-guided denoising network T, and another one is a pre-trained classification network phi. In the training phase, given an adversarial example, we first feed this example to the T network to get a transformed image, TX adver. And then we define the appearance loss based on the clean image and the transformed image, and we calculate the L1 norm between these 2 images. And then we define the perceptual loss, which is calculated based on the mean squared error on the low-level features, of both the transformed image and the original clean image. And finally, we define the classification loss, which is constrained on the predicted losses on both the transformed image and the clean image. And the whole network is optimized with a weighted combination of all these three terms. Now let's see our experiments. So we use the UAE-RS dataset to evaluate the proposed method. So here UAE-RS is an abbreviation for Universal Adversarial Examples in Remote Sensing, which is a dataset we collected in our previous TGRS paper. And for comparing methods, we consider two types. The first one is transformation-based methods, like the JPEG, downsampling, and color jitter. And another type is the denoising methods, including the denoising CNN, CBDNet, HiNet, and the proposed TGDN. So these are some examples of the clean images and corresponding adversarial examples in the UAE-RS dataset. So basically, we can observe some noisy patterns in those adversarial examples. And also for this subset dataset. And we first visualize the transformation images of different methods, like the JPEG and downsampling, color jitter, and different denoising networks. And it's actually very interesting to see that different denoising network can actually well remove those adversarial patterns from the adversarial examples. And here is another example. And we also conduct some quantitative results based on the transformation methods, like JPEG downsampling, and also the denoising ones. We can find in most of the cases, when we use different architectures of the classification model, the proposed TGDN can achieve the highest classification accuracy. However, compared to the Oracle one, here we use the Oracle to represent, we directly classify the clean test set. So you can see there still exists a large performance gap between the denoising model and the Oracle model. And these are the results on the UAE-RS AID dataset. We can observe similar phenomena, and there's still a large performance gap. And finally, I will make a brief summary for this talk. So in this talk, we very briefly introduce one of our recent work, the UAE-RS, where we collect the universal adversarial examples in remote sensing. And also, we summarize 3 possible directions to conduct adversarial defense, including adversarial training or well-designed architectures and transformation-based methods. Specifically, we introduced the proposed TGDN. And also, there are some limitation in the current work that, as we mentioned in the experiment, there still exists some performance gap between the denoising method and the Oracle ones. So we can try to further improve this part in our future work. And we are currently also editing one special issue about adversarial attack and defense for remote sensing data. So if you have interest, we welcome all of you to contribute to this. Okay, that's all for my talk. Thank you.
Very nice presentation. Questions?
It's a very nice talk, and I have a question is that why you complain the appearance loss and the perception loss? Because as we all know, the perception loss is also focused on the appearance, which is based on the grammar matrix. So many people will combine the appearance loss and the structure loss. So why you choose the perception loss? I wonder.
Oh, okay. So that's a very good question. So for appearance loss, what we want to achieve is that to put constraint on the denoising model, so that after the transformation T, we can get an image that look as similar as possible to the original clean image. So that is the L1 norm here, that we directly put on the original clean image and the transform image. And for the perceptual loss, the reason that we choose this loss is because when we design the UAE-RS dataset, that is the mix-up attack. You can see that we actually put some constraint in the shallow layers, and we ask the mix-up features and the original cleaning features as close as possible. and we want to do the inverse way so that we can better fit the defense for this scenario, because the adversarial examples we want to defend from is generated in this way. So we want to do the inverse.
I have a question.
Okay.
So adversarial sort of networks are designed in instances because somebody, a human being or someone is trying to maliciously act against your classifier. But in remote sensing context, it's a nature that's working against us, right? It could be rainy, it could be a bad day, it could be some sort of a inclement weather, or you're driving a car, maybe some sort of, So the question is, does that have an impact on the kind of methodology you go for? I mean, as you're designing an architecture or something, rather than designing against a malicious person, you're designing against perhaps the vagaries of nature that could happen, right? There's a satellite, somebody's not going to go up at the satellite and try to tinker with it. It's much harder. They could do it.
Yes, yes.
But on the other hand, the false positive or false negative would happen because of the natural variation that happens. So are people trying to study the impact of natural variation in the context of adversarial performance?
Yes, that's actually a very important direction. So currently, what we present here is a kind of like preliminary result that we assume that we can get the full access of the satellite images that we can acquire, and we directly put some adversarial noise on those images. But this will be infeasible in the practical application scenario. And more, if we want to conduct more practical adversarial attack, we can consider the physical attack, where we directly to consider different illumination and the imaging conditions, and we think about how we can directly to change the image captured from the sensors directly, instead of after we capture the image, then we put the noise on it. And there is currently only one related paper that I read before working on this. And another work is related to the aircraft, the unmanned aircraft, because for this case, they are actually doing research on the on a kind of object detection and on a car, and they put some materials on the car, and then this kind of material is generated based on some adversarial attack algorithms, and then the aircraft sensors cannot recognize this car yet. So that's a kind of physical attack, which will be much more difficult because of different illumination, and the imaging circumstances may vary in different scenarios. So this will be the future work, but it will have very good application scenarios, considering like a military applications, like you have a military tank or something else, and you can cheat your enemies that their system cannot recognize your.
Just do it for traffic cameras, and you have a startup.
Yeah. That's
Very good. Thank you very much. Again, let's thank the speaker. The next speaker in the session is Peter Pavlík.
My name is Peter. I am a PhD student at the Kempelen Institute of Intelligent Technologies. Okay, there we go, so you can hear me better. And I will briefly summarize our paper focused on precipitation nowcasting based on radar data, and how volumetric approaches can improve the accuracy of the nowcasting. So, firstly, I will give you a brief introduction into the domain for those who are not familiar. Precipitation nowcasting, or nowcasting in general, is defined as forecasting with high local detail, at most 6 hours into the future, but usually even shorter time horizons. And for nowcasting, we need rapidly updated high resolution observations of the current status. So in the weather domain, we can use many different sources. We chose to focus on radar, weather radar stations. So here you can see the weather radar stations in Slovakia. There are 4 radar stations, and on the left side you can see an aggregate map. Basically, the radar stations observe the reflectivity of the precipitation particles in the atmosphere, and then they generate a map like this. Here it's in 5-minute time steps, and it is a rough approximation of how much it rains or snows on the ground. And if you look at it from the nowcasting perspective, the nowcasting task is to look at some images from the past and generate some of these images, how it will look like in the future. So I will also talk very briefly about some related works. I wanted to first mention some representative of model-based approaches, and I chose the STEPS algorithm. It's an ensemble method of probabilistic approaches based on optical flow, and they can extrapolate the movement of the precipitation particles into the future like this. However, we focused on data-based approaches such as convolutional neural networks. Specifically, you can see UNets are used for this task pretty often. Most of you are familiar with UNets, as I've seen today. So it's originally an architecture for segmentation. However, it can also be used for generating future images. And one problem with this model is that it generates one single prediction. And as we move further into the future, the prediction is more and more blurry because there's more and more uncertainty, and if you want to generate a single prediction, that's how it is basically present in the prediction. Then, lastly, I would like to mention a model that's arguably the state of the art currently. It's from last year, developed by DeepMind Laboratory, and it's based on generative adversarial networks. It was compared in the paper to both the approaches I mentioned before, and in an expert study by meteorologists from British Met Office, in 89% of cases it was chosen as the best currently available model. So you can see the data-based approaches show great potential in this domain. Now let's move on to the contents of our paper and what we propose to do. So volumetric nowcasting, why we should do it, and what we did. Here you can see one slice of the radar observation data only at one set azimuth. So normally it's 360 degrees around the weather station. This is just one of these vertical slices. And you can see the data is actually 3-dimensional. It's not just a 2-dimensional plane as we've seen before, even though most nowcasting approaches only work with this data as 2-dimensional. So, for example, they take one slice like this, and then they get a 2-dimensional map. However, this way we disregard any vertical structure of the objects and any vertical movement over time. So, what we propose is using multiple slices like this and generate a 3D volume. This 3D volume can be used as an input and also be expected on the output of the model. So we move on from pixels to voxels, and in practice we get from a map like this to a 3D volume that looks something like this. You can see how the vertical structure is present, how different it's from the top and from the bottom in this animation. And to basically confirm our hypothesis that it should improve the accuracy of the model, we chose to compare it using a UNet architecture. We constructed a basic 2-dimensional UNet for this task as is usually used, and we adapted it to a three-dimensional UNet. So basically we replaced the two-dimensional convolutions with three-dimensional convolutional layers. And otherwise we kept it exactly the same, so it's as fair as possible. We used the same training data, only two-dimensional, from two-dimensional to three-dimensional. And we compare it at the task of predicting one constant altitude radar map, so two-dimensional map. However, with the three-dimensional model, we chose only a single slice from the volumetric output that is appropriate to the model that was trained. We used 2 kilometers above radar, and we compared it at 30 minutes into the future. So in terms of metrics, you can see in the first row, there's just a benchmark, a very simple persistence model. Thankfully, it was the worst from the compared model. And in the bottom rows, there's the two-dimensional and then the three-dimensional model. The MSA metric was the main one we focused on. And you can see the improvement was around 3%, which does not seem that much, but when we move on to visualizations, you will see that it is very clear, the improvement that was gained. So here are the visualizations. There are animations 30 minutes into the future at 5-minute time steps. On the left side, there's the target that we want to get. In the middle, there's the two-dimensional model, and on the right side, there's the three-dimensional model. And as we move on through time, you can see the two-dimensional model gets more and more blurry over time. However, the three-dimensional model really keeps the detail and keeps the the maximum values in there. If you look only at the last slice, at the 30 minutes into the future, you can see the areas with high precipitation really stayed at the same level, and at the 2D model they dissipated, they got lower. This is very useful because in this domain we want to specifically get the high precipitation events, and we want to generate alerts when these happen. So this is especially useful behavior, exactly what we wanted to get. So to sum it up, providing more information to the model from multiple altitude levels has the potential to decrease the prediction error. And also this volumetric nowcast will hopefully provide more information to the operators of these systems. And in the future, we would like to focus on mapping these precipitation maps, be it two-dimensional or three-dimensional, to the actual rainfall on the ground, which is still a pretty open problem. So that's it from me. And if there are any questions, you can ask.
Very nice presentation. Questions from the audience?
Okay, so I have a question, more like the open question actually. You use MSC as your metric for the performance of the model, and it's kind of obviously to use it for UNet, but from our weather forecast competition, we know that it is not the best one. Yeah, and do you have any comments actually? What would be the better metrics? Have you thought about it?
Yeah, the MSC encounters basically the double penalty problem, because when the cloud moves a little bit the other direction than expected, then that would get double penalty, because on one hand you don't have as high reflectivity as you expect on one place, and also you get too high in the other place, and then it gets blurry. So I think the best approach right now is the model from DeepMind. They, as I mentioned before, they basically constructed their own loss function, their own discriminators that also made the predictions temporarily stable over time, and also try to make it look like a real radar image. So I think that's currently the best approach.
More questions here? Yes, please.
Yeah. I guess, and I don't know, this is maybe a question for future work, but what has your experience been in evaluating this approach with respect to extremes? I know modeling extremes, and extreme precipitation, but extreme weather in general is very difficult. That's an area that I'm interested in. Do you think this approach maybe has any clues, or have you seen anything in your experiments that would suggest this is capturing some of the phenomenon associated with extremes that maybe other methods don't capture?
Well, you saw it visually that really the extremes did not get blurry, did not get dissipated, and stayed at roughly the same level. I showed some at the table. There was not only MSE but also some metrics of accuracy and F1, and those were based on area of the precipitation clouds only. So and they were from binarized maps. So I think for evaluating this, you just choose a threshold where you want high enough and evaluate how much it matches.
Yes, so a question in the back.
Yes, I was wondering, you said you're interested in predicting extreme events. Can you say something about your observations of how your models cope as you get into more rare events when your training data becomes increasingly sparse?
Yeah, that's a good question. Actually, from all the data I obtained from Slovak Hydrometeorological Institute, I threw out around 97% because they're mostly clear skies. So, you need a lot of data to train them at extreme events because otherwise, you don't have anything to train them on.
Thank you.
There was another question here.
Yeah. I have a question is that you ask in the future how to apply this into the real case. As we will know, the defined work in nature is focused on how to based on GAN-based to generate all the reliable radar data. And also there have some work, for example, rainfall physicals, how to based on rainfall physicals to get the precipitation nowcast. So what do you think and what you will do in your future? How to apply this in...
Well, the problem we are facing now is that to map these precipitation particles in the atmosphere to the actual rainfall on the ground, you've only got some point measurements on the ground from some meteo stations. So you need to develop a framework to basically map this correctly and adjust the map of the precipitation particles to the map of rainfall on the ground based on these. So something like that. I don't know if I answered your question.
I'd like to thank the speaker one more time. And the next presentation is by Bruno, Adriano.
Okay, hello again, Bruno, Adriano. I have another talk. This is a little more related to our group, RIKEN. I'm from RIKEN IT in Tokyo. This talk is predicting flood inundation based on machine learning and numerical integration. So probably this is some continuation of the talk that I gave the previous session, and probably you already realized that our group tried to focus on disaster response. For that, we rather than use a lot some existing data and some semantic segmentation problem for binary maps, private areas of binary map, we try to propose or address problems that we see during a normal condition or realistic condition of disaster response. Okay. So this is the same area I presented before, but much larger. So actually the flood in this area was very extensive, as you can see by the scale. It's, I don't know, probably 20 kilometers vertical distance. And this is again the kind of nicely interpretation using pre and post SAR data, right, for this event. So red, I don't know if you can see, but red spot are the fire area and blue is in fire area in the urban zone, urban areas. So using these techniques or other techniques, machine learning, using possibly and a lot of data set for training. And we can easily detect these kind of maps, right? We can detect a binary map of where the, let's say, positive pixels tell us the flooded areas or changes areas, right? However, if we take a look here and we try to think in the, let's say we present as a researcher or as engineer, we give this map to some decision-making people, and they try to decide, okay, we have large extent of flooded areas, so where shall we send our resources for evacuation or, I don't know, relief efforts, something like that. So we need another dimension, right? We need to know, or we think we need to know, we need to give much further detail. For instance, in this area that I showed in the previous session, this area shows actually, or this map shows that is the map done by the Spatial Information Authority of Japan, which is the institution or the authority in charge of producing or doing field survey after the disaster. So this is the actual survey, reported survey of the inundation. So the blue color, you can see the range, or the shows the intensity or the actual water depth recorded in those areas, right? So you can see in this area, we have much darker blue, much darker pixels that indicates the flooded area was around probably 3 meters depth, right? 3 meters of water at that time. Or that area was inundated with 3 meters of water. So obviously, we have this large extent, and we have this another dimension of information we can give, or we can plan much efficient relief effort, right? So that is the idea of this research. So rather than just provide, or of course, having an inundation for a damaged area map, flooded map is important, but we also think it's also important, especially with the flood is large, give the partial inundation of the map, so give another dimension. So to do that, we is it moving? Okay. We cannot see that a little bit, but we propose this simple framework for addressing this, or for try to give a solution to that problem. It has let's say two parts. First, the development part, and in here we basically use numerical simulation, and also machine learning as a regression model. So for the numerical simulation, we start by first collecting surrounding areas, I will show later, but running many simulations to create a data set. And we assume rainfalls, as you can see here, and we use the DEM, kind of model resolution DEM, 10 meters ground surface distance. Using those as an input to the some numerical simulation, we can produce this kind of result. This image shows the simulated inundation depth. So from the water level from ground to the inundation, right? The maximum inundation. And this is what we get as, let's say, in the real life. And this map is just a binarization of these images, which is what we can get using remote sensing data, right? Radar, optical, or using machine learning, change detection, any technique, right? So once we develop this data set, we use a regression model to train using the input as a DEM and the mask that we can get from remote sensing, and try to get this inundation. That is the concept. So once we have the model trained in a deployment phase, so when real inundation happens, we can use SAR, in this case I use SAR, but we can use other remote sensing data set to get this change detection map, the binary map, which shows white pixels, the flood areas, and use together with the DEM, corresponding DEM, we can provide this kind of prediction. So this is the inundation, actual inundation, water inundation, and this or in the target area or the study area. Okay, so that is the approach or the framework we propose for this problem. This is still a preliminary or early results of this work. So, okay, so first, let's go for the simulation part. So to construct a data set, we selected, actually we selected many, but we could present here four target areas. So all in Japan, we are from Japan, of course. So we have, these areas are historic, they were affected by flood in the past. We have Ibaraki, okay, Tokyo is here in the center. Baraki, Okayama, Hikawa, and Umachi. So to set up the problem a little bit more realistic, we select 3 areas for training validation or model later, and we separate Umachi city, which is in blue, as a testing. So that the data or everything from that area or from that side will never use in our development. We will keep beside just for testing to see if our model generalizes well, if we can have some reasonable prediction of inundation. Okay. Okay, so that is the inundation, right? So we use later we use the RIKEN model. This is a model developed by Acham Institute, also in Japan, which is do the numerical simulation of flood inundation. So this slide, I don't know if it can move, but is it moving? I'm not sure. Okay, this animation supposed to, yeah, it's not moving. Sorry, I prepared this in Mac. Okay, anyway, so this, if the dimension show how the water start to appear here and start to flood. So again, we use a constant DEM. For this is one target area, and we assume many rainfall scenarios, a rainfall distribution, just random. So we don't use historical data of the previous event. We try to generate very, diverse scenarios of rainfall that produce some inundation, right? So this is one example. It's supposed to be one example of that simulation. It's not moving. Okay, let's continue. Okay, so something like this. So this is the simulation, some scenario for our training or our sites that we use for training. And that is the scenarios that we use. So the numbers are different because actually we run around 700, we say 700 scenarios for rainfall, but for some rainfall did not produce any flood. So that's why we exclude. We just take the one that could produce some flooding, representative flooding, right? So there is a scale, but maybe the display doesn't help. So some of them are very low, very like a 1 meter depth of flooding. So we said we cannot use that because that's not much representative. So we use just the one that have higher flood, moderate higher flood, and kind of large extent like this, right? So these are the scenarios. And then from this, obviously, we cut this into patches, so nice for a machine learning model, right? Okay. Okay. So this is the actual example of our data set after cutting an area of 500. I think it's 500 meters squared. So on top we have the simulation. That is the output of the RIKEN model. This is numerical simulated. And the second row is just the binarization, right? And this is the third one is the DEM that we use to simulate this, the top one. And just to compare, we use a simple responder method that using DM, right? Just assuming the maximum depth and subtracting from all the area inside that. And so all the pixels inside the inundation area, right? And then we can see very, very clear difference, right? So on top, this is a simulation. It follows some dynamic process of the flooding, right? But this is just static, just cutting as a threshold, some horizontal value. So that's why, for instance, in the second column, we can see the inundation is about, simulation one is about 2.5, 2.6 meters depth, but this goes to 9 because it's just a simple thresholding. Right? Okay, so, then once we construct the data set, we go to the machine learning part. So this is training the model. So the training is simple, right? We have the simulation one. Based on some thresholding, we can get the mask. In this case, white pixel shows the area that is flat or was flat. And then using the DEM and the mask, we just go to some UNet type architecture and call the decoder and try to reproduce or find some regression to get the inundation, simulate an inundation. So we do that process many times when those 3 sites that I showed earlier. And like to see this the results on the test data set. This is so much. So this data set was never used for training, remember, okay? So we have consistent result. We are happy. So top is again like the ground truth, the simulation one. And the second one is our prediction, right? It's consistent, right? Very consistent, I would say. And this is just a difference. So of course, as a difference, there is some errors, right? But the errors is about 50 centimeters. So I think it's working, not perfect, but it's working to some extent. And we also, we input, in the previous one, just used the mask and the DM. And for this prediction, we add the flat as a thresholding. So maybe we thought, let's give the network a little bit information how the inundation should be. So three channels, but the results are similar. So it doesn't help much, or it didn't help in this case. Okay, so this is more results. This is already some numbers. So we tried 3 standard networks. Like I said, this is just starting of trying our concept. We didn't try any transformer or fancy network now, but we are planning. Again, top the simulation, which is the ground truth, prediction for just using mask and DM, and it works, right? It's consistent, and but still, all this is still synthetic data, right? This is simulation. This is actually not real case. So for synthetic data, of course, we know machine learning works, and this also works, even though these are different area, right? Different environment, different topography. Oh, okay, it's working. So now I give you it's moving now. Sorry, one example. This is one area that was not included in our sites. It's another area, and this is the red pixels again show the flat area, and we can get a mask, very simple. And using this mask and the DEM, this is what our network created. This is just totally different area. It has the blue range shows the inundation, right? And if we compare with the map, what happened? This area is, sorry, map is, that area is around here, but I wanted to say that the map that showed, recorded by the institute in Japan, shows very consistent result with our case. So we were happy to see that this early experiment showed that this concept works using just simple CNN architecture, already standard UNet or LinkNet is working. And you have any question? I'm happy to answer. Thank you.
We have time for 1 or 2 questions.
Thank you for this impressive presentation. Sorry, maybe I missed it. Did you have already labeled data of the depth of water, or you just overlaid with the DEM and calculated?
Yeah, we wanted to. The reason that we selected those areas because, like I said in the beginning, those areas already have some flood, and we tried to collect. It's very hard to collect those flood inundation, right, of the flooding. Even though we are in Japan, it's not easy. But for this case, the label was created through simulation. Like I said, we ran the simulation. And then we create this. So we haven't compared actually with the real numbers. So the last slide is supposed to show some comparison, but I don't know what happened with the last figure. It was.
Can I ask what is the resolution of your DEM?
The DEM is 10 meter resolution.
And have you ever used DSM? Because when I see your last slide, I mean, when you have some buildings or borders, walls, this can be influence the inundation of the flood.
Yeah, that is true. That's a good question. So that's why we actually, that was one motivation of this. When flood happened, especially in Japan, when we use Sentinel-1, for instance, that we only detect flood in the plain areas, the paddy fields, agriculture areas. So flood in the urban area is in the example I give is nicely detected. It's blue, light blue. The processing was nice, but in most of the cases, the detection of the flooding and detection of flood areas in urban places is not well done. That's why we try to use much higher resolution. We didn't try DSM in this case. Yeah, but probably there's some other direction we can try.
All right, with that, let's thank the speaker again. Now the highlight of the meeting again with the keynotes by Nebojsa, Jojic.
This talk is going to be a little bit different speed than what we've listened to this morning. And I have to say, since I'm the last one, I really enjoyed all of the talks. I've learned a lot, and I'm looking forward to the PDFs on the website. But this is going to be a little bit different. I'm not going to talk about the latest models or even very creative combinations of data sets or new applications, nor am I going to emphasize how important geospatial analysis is. And when I say scale, I don't just mean compute and cloud and storage, although that's a part of it potentially, but I'm really talking about scaling it to, in terms of the human use, scaling it to more people with various levels of expertise, with more applications, with more creativity and so on. And I'll try to make it clearer. I'm going to flash this sort of overview, but I'll come back to it because hopefully it'll make a little more sense a little later. But one thing that I'm going to insist on is that we're actually not very close to the data, even though it's all there in the cloud. We have it in AWS, we have it in Google Earth Engine, we have it in Planetary Computer, MSR, or Microsoft, and so on. But it's kind of far in terms of how quickly you can get to it. The access it would be better if the access was kind of ubiquitous, fast, low overhead. And it would be good if that would include all sorts of data, including data from satellite companies that you have to pay for. But you have to somehow be able to see the data before you decide what you're going to do with it. The other thing is that there should be a possibility to do real-time exploration through computing. So instead of running very complicated, very expensive models, training lots of data, can you somehow in place run very quickly, very simple models and gain insights about what you could do with this data based on that? And the third point is that we should build for humans, and that involves visualization tools, good UIs, allowing even non-experts to use these algorithms through something that's a map-based interface, ideally, that looks more like what you do when you're searching for directions to a restaurant on Google Earth than what you're doing in Google Earth Engine when you're running a task. And in order to make that point, here's a semi-serious challenge to the audience, to the geo-wizards in the audience, which would probably mean the younger people in the audience. And the motivation for this is that really, I mean, it's the age of the cloud. It's all there, right? It should take seconds. Things should take seconds, but those things that should take seconds. Do they take seconds? And so here's a challenge for you to try to do during your talk, this talk if you have a laptop. Or by the evening. Get Sentinel-2 imagery of the Vienna area. It's just 400 square kilometers. As Vienna has been important in the modern history of humanity, it's relatively small, 400 square kilometers. That's at Sentinel resolution, that's like 4 million pixels, 4 megapixels. I can get that with this. So it's not big, right? Find it, get it. Then cluster all the pixels into 20 clusters. Then make a browsable map. Just send me the link. Hopefully I can get the link into this computer. And then we can browse through a web browser. We can browse and see what the clustering of Vienna looks like, right? You can send it to my email, and we'll see. I mean, whether somebody solves that challenge. What do I mean by browsing link? I mean something like this. You have, you go to this is done by Caleb, one of my former interns and the organizers of this workshop. And this shows a landcover map we created for Seattle. And there are a bunch of layers there, and so you can flip, for example, to Nate, so you can sort of see. So you can create something like this in any tool you want, however you want. That will just show clustering, unsupervised clustering of pixels in the Vienna area. And while you're thinking about it for a second, let me kind of switch gears completely and play a video that's completely unrelated. So let's see.
Welcome to our lane cover mapping demo. This web application allows users to perform 4 high-level operations. First, users can run our lane cover models by simply clicking around in a Google Maps style interface. Our backend server uses a deep learning model to classify each pixel in high-resolution satellite imagery as belonging to some lane cover class. The lane cover predictions are painted on the screen, and users can quickly explore how the model performs in diverse areas using just their browser. With this capability, it becomes obvious where the model is making mistakes. In this case, we can see that the model is misclassifying this boat dock as belonging to the water class. This motivates our second high-level operation, model fine-tuning. The user can correct mistakes like these on the fly by selecting a training class from the panel on the right, then clicking on the map to provide examples for that class. Here, the user is adding training points to indicate that the boat dock should be classified as a built surface instead of water. Clicking the retrain button will fine-tune, then rerun the model in the previously selected area, taking into account these new training points. We can see that the model's behavior has changed, and it is now overestimating the built surface class. This can be corrected just as before, as the interface will allow the user to quickly iterate and tune the model's behavior. Here, we will give the user some time to find and correct a few more of the model's mistakes.
This music is not good for my jet lag.
This is Caleb, huh?
This is Caleb, yeah. This is our AAAI paper for 2020. And there's a lot to be desired, but I'll tell you why I'm showing this in a second. Definitely not the best way to do this.
After several cycles of providing new training points and fine-tuning, the model's outputs are acceptable despite never having seen this area in training. Our third high-level operation extends this fine-tuning capability to new classes. This area is wetlands and doesn't fit well into any of the lane cover classes that the model was trained on. Currently, our model is confused here and is predicting a mixture of field, water, and built surface classes. Users can click the Add New Class button, select a new color, then, just as before, provide examples of this new class. The retraining operation will result in a model that predicts the new class, wetlands in this case, where appropriate.
So this video goes for another couple of minutes.
We can see that the new wetlands class does not infringe on our existing classes. Furthermore, we can see that it's recognized even in distant areas.
I'm going to fast forward this a little bit. Wait. Maybe we'll just let it go because I can't fast forward, it seems, in this interface. Now, the video is about 2 minutes, and by the end of the 2 minutes, Kel will have this huge area of Chesapeake classified. I don't know what the accuracy is. Since then, we've decided there are better ways of doing all of this.
Is the ability to run and download results. Once users are happy with the performance of the model, they can press the download.
But I'll tell you why I'm showing this and what I like about all of
provides
this.
the results is a georeferenced TIFF file and PNG. This data can be directly incorporated.
So the first thing that I like is the speed. So some of the functionalities have been kind of reduced a little bit just so you can get the speed. So you don't show the classification of the entire area all the time, but you have to select where you want to see it. Your eyes travel around, you study the terrain and decide what you want to see. Then the model computes this so that it gives you back the result in a second, so you don't lose interest while you're doing this. The second thing is you have to ask for retraining. Why don't you just retrain after every click? Because again, it will take a few seconds and the magic is broken. So the whole thing is just fast enough so that it feels like interaction and not like running a job on a server somewhere. So that's the first thing. Then the second thing is, you think about what was going on here. The the whole machine learning paradigm is kind of the usual supervised machine learning paradigm. Anyways, it's kind of flipped on its head. The user here is Mechanical Turk user. We've run it study on 20 people. And they are the labeler, and they are the modeler. They fine-tune the model. So they're doing both things at the same time. It actually turns out that as they're doing this, they're starting to kind of develop a theory of mind of the model, and they kind of know how to find the best points to fine-tune things. So then, what we are really kind of getting here is that, and I'll tell you what the third thing is in a second, but when we ran this with Mechanical Turkers, it turned out that you can make plots like this. What is the performance with time on the tool? So this is like 15 minutes. And in 15 minutes, the users were supposed to create a map of about 80 square kilometers in Chesapeake area. And that was at 1 meter resolution. So it's actually 200 times bigger than the Vienna area in terms of pixels. 5 times smaller in terms of the actual area. And in 15 minutes, they would get to that sort of a level. And so we were estimating that if you look at the best of these 20 users, they could have mapped the entire Chesapeake watershed at a cost around $20,000. And Chesapeake Conservancy actually spent over $1 million in 9 months to do it. But then when you talk about it that way, suddenly it turns out, well, it's the human time versus accuracy, right? And that's always the case, because you always have somebody labeling things for you. And then you have an army of students and data scientists fine-tuning the models. There's always a lot of human time involved. So if you think about the process being human time versus performance, how much labor, how much time is necessary to get to the desired level of performance, then your thinking changes quite a bit, because then you can improve, you can push this curve up in different ways. For example, just making better UI, having simpler models maybe, having an ensemble of models instead of one model like what we're training here. You have all sorts of options.
Do you have any idea why the mean user is worse than random for the first 2 minutes?
Yes. So as I said, there's a lot of things to improve in the interface. And one of the things that are problematic in the interface is that thing that Caleb kind of brushed over, that whack-a-mole effect. When he defined that dock to be impervious, suddenly all water became impervious. Then he says, well, water should be water, not impervious. Then a lot of impervious becomes water. And so he plays this whack-a-mole game. And until you realize that there are certain things you should correct and certain things you shouldn't correct to actually influence the model. And at that point, you become sort of a data scientist, like these people who won the competitions, right? They have that feel about what the model will do. And the user actually develops the theory of mind and then starts going up. So that's basically the reason. Now, if anybody started doing the challenge, which I see everybody's slacking off, but if anybody had started doing the challenge, you wouldn't be looking at images at this point at all. This is what you'd be looking at, something like that, right? And data visualization would be something like this. So it would be a very, very different, and it would take you, Caleb actually took the challenge and it took him 20 minutes, and he was happy about it. He took the challenge at 9:30 p.m. and was done before 10, so he was happy. But in 20 minutes, and clustering that number of pixels, I would do it in less than 20 minutes 30 years ago, in MATLAB on, an old PC. But most of the time was getting the data out. And then in the end, even the interface you get from Google Earth Engine is very clunky. It's not this fast at all. Now, what I was saying is that we should save labelers' times, but data scientists can also use their time better. And this is not the way they should use their time better, it's just the evidence that they could. And so this is from a competition we organized with Pedram and others at IEEE last year. And the challenge was to detect change between two data points, two time points. And the competitors were given two naked images. And coarse 30-meter LCD land cover maps that were not quite for those times because they were not available for those times, but a little off by a year or so. And that's all that they were given. And they were supposed to figure out what the change is and make a map that would look like that, where most pixels are black because there's no change, and then color coding shows different types of changes. Now that video is going to be looping hopefully, and it isn't a video of change. It's because there's only one change, one step in change. It is actually how that change has evolved during the validation phase of the competition. And what we're showing here is the consensus from all the competitors, like between the 50 and 100 teams. You know how these competitions go. And so what that is showing is how consensus is evolving towards the end of the competition. And what the graph here is showing is from the beginning of the validation phase in January till the end, 2 months later, right? The blue shows the best user score on the leaderboard. It's going up. And then these two other lines are basically voting ensembles, simple voting ensembles. And the red one is a voting ensemble, but the other voting ensemble is actually not including the top 3 at all in the whole time, right? Now, note that the voting ensemble, even without top 3, within the first few weeks is reaching the level where the best person is at the very end. What does that mean? Well, the competition was not organized for the purpose of labeling the entire area. It was organized for the purpose of people competing who's better data scientists. And for that purpose, we got the result. And they had excellent and interesting algorithms, and we got what we wanted, nice, interesting algorithms. But if our goal was to label the change in the entire Chesapeake area, then we should be using data scientists' time better, obviously. They should somehow be working together. And this is without them even communicating with each other, right? If they could communicate somehow, that should be better. Now, and what about the program manager's time? And so now I'm going to describe some experiences I've had over the last few years, and I'm sure a lot of you have, especially more senior people get to talk to customers or what are collaborators setting up, the project. And typically, you get to talk to somebody who's smart, but doesn't have computer science background, can't write these scripts, but has a good idea about what they should do with the data. They might come to us and say, well, we want to count cows in California or Africa. We want to count all the solar panels. Could you use Sentinel-2, 10-meter resolution? Maybe through time you see some flicker because of the different angles. Maybe you can see something. Maybe you can't. It's too small. Cows, clearly everybody agrees you can't see it at Sentinel-2, but can you see it on planet with 1 meter? You have to go to Nexar with a better resolution. And so these discussions are usually completely blind. Like we talk over the phone or in person, and we discuss what might happen. We never look at any imagery, right? So if we had the interface I was talking about, we could, in every meeting, we could go and look. And not only that we go and look, we can run some simple algorithms to see whether something is feasible. That sort of person I call a program manager, but it's a variety of people in agri-food companies, in non-profit organizations, in government agencies, energy companies, banks, and so on, who could use not exactly Caleb's tool from before, but something that feels like it, that it's much better, and it has all sorts of layers of data that we have, and derived data, the sort of stuff that people have actually already computed and stored. And they could spend an evening browsing through things and get a much better feel as to what's possible, and be more confident that they should, for example, buy some of the satellite data that they have to pay for and so on. So now, with that in mind, that's what I meant by all of these things. We should be closer to the data because all sorts of people can use this, but even we can use being closer to the data because we can debug things faster. Then we should be able to do real-time exploration through computing without writing a script, just picking up clicking on a pixel somewhere and say, like in that tool, or saying cluster pixels in this area, there are certain things that are immensely useful. Clustering either Gaussian mixtures or k-means, PCA, some very, very simple, useful tools, which you can then apply to get the first level of result. You're not going to get state of the art, but if you can get 80% on the way to the state of the art, but for virtually zero time effort, that's a big gain. And finally, for humans, you get the idea that the interface and friendliness to people who can't and don't want to wait or type things. They don't want to cluster Vienna in 20 minutes. Now, how? We can leverage structural Earth observation data, both for fast processing and storage. We can build appropriate UI, but the difficult thing is that we will have to figure out data sharing structure. That's a difficult thing, but I'm sure it's doable if other things are resolved. So what do I mean by leveraging structure? So this really quickly, what does the Earth observation data look like? Well, we have imagery at 1 meter resolution, but it's kind of rare across time. We have 4 channels here in APE. It can vary over time quite a bit. Then we have 30 meter resolution imagery that has more channels. You get it every couple of weeks. Sentinel is even more frequent these days, but you have clouds. But then you have data that's sort of like this, where instead of having these dense grid measurements, you actually just have a few sparse points. This is the JEDI LiDAR used to estimate canopy height, but it's not only in these sort of footprints. And the darker blue, I don't know how well you can see from there, but the darker blue, like the one you see here, is a taller tree, and white is very low land area, and this sort of sparse type of data, where it's just a point measurement. Other examples that would be like ground sensors, something like that, or this. This is from iNaturalist. Are you guys familiar with iNaturalist? Yeah. So these observations of sea eagles and fish-eating eagles around Seattle, and you can see that they're kind of close to the water, so you can use that as a proxy for water classification if you wanted to. So and they have all sorts of stuff. They have mushrooms that typically show up on the edge of a forest after rain when the sun shows up. And so all sorts of things that you can relate to whatever task you want. I'm just using it as an example of sparse observations. But generally, geospatial data is grounded, with pun intended, although I hate puns. And you can have these multispectral satellite dense imagery, or you can have drones that are much closer to the ground, better resolution. You can have ground LiDARs, you can have these sensors, like for example, moisture sensors in farms in a few places, or weather stations and so on. Some of this stuff actually is a Microsoft product called Azure FarmBeats, obviously for agriculture. But the point is that it's geospatial data is basically varying quite a bit in temporal density, spatial coverage, resolution, precisions in terms of when it comes to local sparse point measurements. Precision can vary. You have different types of measurements, but it's all registered in that long time, which means that those interfaces I was talking about shouldn't be that difficult to build. And all of this data is also highly correlated. So storing it and retrieving it and rendering it quickly might also be possible with appropriate compression algorithms. And then we talked about in the first invited talk by Vipin, we talked about, or he talked about how labels are always a problem. All right, you might not have the labels you want, but different types of labels are scarce. But in terms of their structure, it's the same story as for observations. You've got high-res land cover, but you usually have it only in a small area, like Chesapeake Bay here, and you have. This is just showing you what the corresponding image is. You have NLCD, which is a 30-meter resolution, has more classes, but it's actually assembled every few years. These 5 years that I put there, that was the longest, actually. They quickly afterwards made 2016 and 2019, I think. And then you also have sparse measurements. Like this is actually the map of where people clicked in that tool, in that experiment I was talking about. They were not random. Obviously, they click into the water a lot because of the whack-a-mole effect. But you'll see that they kind of click into a few different places where there are different types of trees, a few different types of impervious surfaces, and lowlands and so on, and then that's the data you need to classify things. So then, both Earth observations and labels have that same structure in terms of variation, and they're both registered in lat long and time. Labels, of course, are much scarcer. So, what makes me hopeful that you can not only store all of that and retrieve it all quickly, but also compute new things on the fly? Well, the first thing is that you can integrate different sources that are available, and you can do local computations. You don't, as Vipin was saying earlier, you don't have appropriate data everywhere, but you have some label data or some knowledge almost everywhere. And so you could be doing your analysis in place, just local analysis with simple models, only that stuff. And so, so I'll give you examples of that. So this is from a paper we're presenting next week at UAI. And it's just one example. I'll then cover super resolution, and Laura Elena talked about something similar to this. And the idea is that you might not have labels, but you have some prior belief. And in this case, the prior belief comes from 30-meter resolution land cover, which has these classes. Some of them are mixed, like when they say develop low intensity, I believe that means 30% chance that it's actually built. And the rest is sort of applied to vegetation mostly, but there's a small probability of water. So you can treat it as such. Also, because 30-meter, you should, when you upsample it, you have to blur it first, because this is not a real boundary between, pasture and wetland. You have to blur that. And then the vector data from OpenStreetMap, you can be a little bit more certain, but because of misalignment and so on, you might want to blur that a little bit too. And then when you compose these two, basically average them, you get this. This is your prior. Now, this particular model assumes that there is an unknown generative model that we never estimate that will sample a label from here, and then from that label, sample appropriate texture there. Instead of parametrizing the generative model, we parameterize the posterior model. That's why we call it implicit posterior model. And we get a result that looks like this. This is what that parameterized posterior model does, but this is the actual posterior. And can't quite see very well in this light, but there are new structures that are being recognized in this, as opposed to most of our other models. This kind of gets some reasonable idea of where the wetlands are and so on and so forth. But the main point here is not how we did it and whether it's better than the other algorithms or not, is that this whole thing actually is a local computation thing. We typically use tiles of this size, which is less than 10K in each direction. And you basically just take this and this or whatever other source of prior you have in that area, and you run a computation that gives you this. You don't train on triplets like this. There's no training on other data. All you're doing is combining these images by computing some parameters that represent them well, and from it you get this. That means that it is possible to simplify this. One simple way of doing this is to simply cluster all of the textures there, and then use these statistics of which texture falls into which category, and assign the labels. In fact, 2 years ago, we won a DFC challenge using basically just that. And that can be very fast. So here is just the same thing, just a line. This is the nape image, this is the NLCD, and this is the super resolved land cover. The same thing you can do with that Jedi canopy thing that I was talking about. You have these measurements of canopy height in sparse locations, but if you assume that wherever you have dark blue, whatever texture you see underneath, if you see that same texture somewhere else, it should also be dark blue. It should also be a tall vegetation. And when you extrapolate that way, you get something like this. You get this sort of nice boundary where these fields are here around the river. You realize that these built areas over here are low, but you find these patches of forest. And that's the same idea as I said before. Because of the fact that these are two different algorithms running on these things, there are very fast and simple ways that are kind of ubiquitous. You can apply them to various things that would give you a result that may be worse than this, but good enough if you're going to go to a meeting and discuss with somebody, can you actually estimate the growth of a forest using JEDI? So, this should be, minutes, not 3 months as we plan to do it. Another example of this is this thing that Peter Olsen did. He calls it space eye, and you can kind of barely see it here, but in 24 days, there were only 2 Sentinel-2 images which were kind of clear. The rest were at least partially cloudy. But then if you add Sentinel-1, then those basically are less sensitive to clouds. So you have some texture coming through. And if you now make that same assumption that the similar textures in one channel correspond to similar channels in the other image, similar texture in the other image, then you can copy these textures around. He uses a deep learning model, and you also assume that the changes are slow in time, and then you get what Sentinel-2 should look like if it was always there, and it was always a clear day. From that, you can compute NDVI and try to work out what's going on in the farm. So those were examples of integrating different sources, and I'm arguing that you could make cheap versions of this that would be worse than the state of the art, maybe 80–70% there, but literally almost zero time. Another way you can accomplish that is by reusing previous computations. And I partly kind of addressed that because I was talking about that you could, in all these examples before, it is the self-similarity of textures in the image that's the key. So you could compute some representation of it, like clustering, and then use it in every one of these applications. And you've probably all used things like this. And actually, in the last talk, there was something very similar. But I do have an example. This is a dam in Iowa. And this is the corresponding nape image. And if you look at these sort of areas of lowland, I don't know how well you can see, but in those areas is where farmers often build these grassed waterways. These are kind of low channels covered by grass to collect the water and avoid runoff. And then there are some features that you can barely see. If this was a darker room, you might barely see some slits here. And those are basically farm terraces when you look at them from above. They're basically land like this, but from above you barely see them. They're also built to preserve water and prevent runoff. Oh, that's much better. You can see it now. Now, if you do, somebody has talked about this actually. If you take this crop data layer and run that label super resolution, you might get something like this. And note that all these grassed waterways actually are creating a problem because they look different from the nearby texture. So the algorithm realizes that's not a crop, but doesn't know what it is. So it assigns it to some other class. And so if you want to have a high-res CDL, then there is a post-processing step or some parameter messing with that you have to do to avoid it. But this is sort of an artifact of previous computation, and it's a wonderful opportunity for us to detect waterways. And the way to detect waterways is to combine this thing with that. The basic idea is something very similar to just a layer of a transformer, is to say, I'll take, for every pixel in the image, I'll take, for example, this pixel, take a neighborhood around it, take all the other pixels that have the same class, and average their DM. That's sort of like taking key and queries to be the classes, and the value to be the DM. But if you fall here, you will take only the white pixels here and average their DM. So when you do that for all pixels, then suddenly these grassed waterways show up as really low areas surrounded by high areas. So that becomes a very useful feature map. Another useful feature map is simple gradient of the DEM, where you can see these sort of guitar strings like structures. Those are the terraces. And so if you look at the targets for detecting grass waterways and terraces, you can see that if you look at the red parts, you can see that they correspond to those grooves. These grooves in DM. And then if you look at the green, you'll see that they correspond a lot to those thin dark lines in this DEM embedding. So then when you combine these features plus NDVI and train a simple network, you get these targets, which are fairly good. But if you listen to how we created the features, you will realize that this is actually more likely to transfer outside the biolog where this was trained, because all of these things are normalized, much less dependent on intensity, because intensity was only used for clustering, for local clustering. So even if you transform all the intensities by multiplying by 2, running through some nonlinearity or whatever, the clustering will probably stay the same. So, so now this is a little plug to something that I don't want you to think that this is the solution to everything I'm talking about. It's a small part. We've been working on it for the last 6 or 9 months or something. And this will address this issue of combining different things, different operators, as well as storing the old results. And basically the idea is that you have a platform that can ingest all sorts of raw data sources, planetary computer, for example, which will give you your Sentinel and so on. Then maybe FarmBeats, which has some weather and satellite information as well. Custom data, potentially some drone data. That's what Visage is actually. I was confused when our collaborators first mentioned it. I thought it was something else, but it's actually drone data. And then it's stored in Azure Blobs, and then we built some structure on top of Stack there, but also the computation can be run with these Stack operators. And then the important thing is that you have a cache layer. So when you call an operator, if somebody has already called it, if there is a result, then you don't do the computation again. You just download that thing and continue. And then, of course, you can build APIs on top. And that thing that I talked about with conservation practices will build with these operators, but also more complicated things that have to do with carbon capture and so on. Now, what is still missing in this is this sort of speed, the snazziness I was talking about. And that's actually what we have to do. And so in summary, this is what features of a system that's something like a thinking atlas. I call it thinking atlas because it's sort of a hybrid intelligence. Like a bunch of people are contributing to it, computers are contributing to it. So it's a hybrid system. So one thing is that there are many sources of data should be in that system. There should be many models, some results cached, and then there should be these user interfaces I was talking about. It's not just human in the loop, but also discovery of resources directly on the map. And maybe you can even contract out the tasks directly on the map. So that Smithsonian program manager who wanted to count cows in California could go and outline where he wants the cows counted and see who's going to come and try this out. And if they actually had some simple tools to begin with, they can be more confident that this is possible, and they can even specify how much money they want to pay for a certain accuracy, because they know the low bar. But to do that, of course, this has to be fast. And this has to have a short feedback loop. If you have to wait, depending on the application, depending on what you're doing, if you have to wait a few seconds or a few minutes or a few hours, some things you can wait a certain amount of time, other things you can wait only a shorter amount of time, but you can't there is, for each of these things, there is sort of a sweet spot that if you get out of, it breaks the experience. So the feedback loops have to be sped up, and that, as I was talking about it, that can be accomplished in various ways. You can simplify the models, you can do more local computation, you can make better UI and so on. We should target data scientists. This sort of thing would be wonderful for all of us for debugging, developing new algorithms. But it would be good to also directly target the customers. And the customers could be anybody. It could be actually somebody who just wants to track their lawn over time. Yeah. And then this ultimately could become a market for information and labor. Now, so the next steps then, fast global visualization and interaction tools, where you can cover the whole globe and at least a certain minimum amount of different data layers that you can start with on any task. Faster, near instant local computation or retrieval, and near instant in terms of human experience, people who want to tinker with this. Data sharing tools would be difficult, but eventually have to be worked out because those mechanical turkers have to be paid, but also data scientists have to be paid. Planet will not give images for free, so there has to be a way to track the value as it's being developed, as you add value by processing these data and kind of pay back. But I think if this first bit is developed, then that second bit will sort of emerge because there'll be enough interest. So who should do it? Well, cloud providers are the obvious suspects because, Google's, Amazon's, Microsoft, because they have the computation, they have storage and so on, and RBO data scientists, some AI tools are integrated and so on. But, on the UI side, Esri is very good at UI, but it's very slow. Even their UI is complicated and slow, clunky compared to what I was showing before. So they have something to do. But on the other hand, I mentioned the iNaturalist, and that was started by academia. So, and that's wonderful. So who knows? I don't know who should do it. The actual real question here is, when do we get excited about doing it? Do we just think, okay, well, that's cool, but it's too much effort for very little because I still know how to use Google Earth Engine or Planetary Computer and soon TeraWipes that we're talking about, and I can just do that. And I don't even notice that I've spent 3 hours doing it because I enjoy it. And I'm the only one who can do it, so, and a small number of other people, so why not? So you might think that there is no need because we've done everything we need. Like there is cloud. We can store everything in one place. There is computation for you. There are algorithms. There's GitHub, right? And so why do more? We can just leave GitHub talking to GitHub, to humans. So why do anything? And I would argue that in the past there were many of these sort of turns in technological history when we thought, well, what else can you do? There's nothing needed. We've covered everything. And then there was a huge change, like, PCs before Windows, electronic commerce before Amazon just destroyed everything, for better in some ways, right? Or internet. You remember internet during Alta Vista? Anybody old enough to remember? Directory structure of the internet before Google, right? And maybe my favorite example actually is digital music from the turn of the century. We got digital music because it stores better, and CDs don't stretch as well as much as records. But as soon as we made music digital, then you could share it. It can be on your hard drive and be played on your PC or Mac or whatever. It can be on the internet. It can be shared. You can post your favorite music, digitize it, post it on your website. Somebody can find it. And so, what should, say, Google do about it? Well, nothing. I mean, it's just another data type. We index everything. What should Microsoft do about it? Well, nothing. We made WMAA. We support MP3. You can store it on your hard drive and play it. Do whatever. If there's a new device, you can do the same thing on the new device. We've covered our thing. But back then, if you wanted to find the music you wanted, it would take you 20 minutes, just like clustering Vienna, to find what you wanted. And then you have to also find space in your disk for it and erase something else that you're not listening to. And it's a completely different experience for today instead. anything that was ever recorded, you can play anytime, and you can easily find it. And actually, you can even create music and put it on the streaming services. And the number of high school kids who actually do it in the US is not insignificant, actually. So completely different experience. So if we believe that we can do this, not for entire world, but at least to the next sort of set of people, like the end users of our stuff, instead of just data scientists, then maybe something like this should be built. So that's it for my talk.
Any questions?
Okay, yeah, maybe thank you for your nice presentation. I'm very interested to the demo that you show that the user click the buttons and train the network by itself. Maybe very stupid question. In traditional neural networks, we normally will fix the dimension in the output. So that is the number of categories, like the FC layer, fully connected layer. The last dimension is the number of categories. Or in a fully convolutional network, the last dimension of the convolution layer is also the number of categories. And I noticed in the demo you show that the user click the button like add a new category and then retrain the network, and it will just with several seconds it will output a new model. So that seems it's not a new model. That's you modify the number of categories, but you directly change something and it works.
What I didn't talk about is that first of all, even if you're keeping the same classes, we are only fine-tuning the last 2 or 3 layers. So that's the first thing. The second thing is that if you want to introduce a new class, only the top layer is changed. You introduce a new class, you set some random weights there, and then you train not only on, I mean, it's always trained on previous points as well. So on all the points that you were given. So if he had done this, starting with a new class and not kind of fine-tuning the others, then the tool would break. Now, if you want for it to not break, then you have to have some fine-tuning sort of preset data that you start with, minimum set, which you can generate from the model as well, just randomly. But yeah, that's basically how that happened.
Okay, thanks.
Okay, thanks a lot for a great talk. I mean, and inspiring actually. But to me, what you described is like kind of the scientific utopia. So everyone's sharing data, everyone's sharing models, the way that you can reuse them.
Yeah.
But the reality is different, at least on AMP now. So I don't know, people spend months to prepare data sets, annotate it, download data, and they don't want
somebody
to.
takes it for free.
Yeah, exactly. So they don't want to share it. I think 2 years ago, even there was like the concept called like scientific parasite, which I completely don't agree. Like people using the data of someone else's. And I mean, the competition here organized by you or by RIKEN, kind of the example of good practice when you actually share the data. But what should be the incentives, in your opinion, to the scientific community, or how can we actually make it better? Because
well, the incentive is sort of the long game. When you explode, then there is much more economy for everyone. So that's the really long-term incentive. But if there is critical mass of people who want to build this, once it's built, then the rest, everybody will have to figure out how to benefit from it, and the data sharing agreements will have to be shared. And an example, the reason I mentioned digital music is because of that. If you remember back at that time, there was Napster, that was illegal, it was shut down. Then Apple pushed and figured out a way to roll out iTunes and iPod at the same time. So things worked out because there was a huge gain to be made. There was no turning back. It's there. Similar example is sort of wearable cameras. If you right now, everybody's busy about it, a little bit of privacy, this or that. But if we all had them and we had great applications for you capturing everything you ever see, then at some point you would have to work out how to solve the privacy and so on. In fact, this whole field that we are in, Earth observation, could be destroyed by privacy. The reason why it's not is because it's useful, right? But it could be totally destroyed by privacy, right? So these things, as I said, that's a hard question. It'll have to be resolved. But I'm thinking that if these other ones are solved, and you suddenly see, because it's one thing for me to talk about it. And the reason why I showed the video is that you should see something instead of listening to me. So you can imagine more, much more, right? But once everybody sees something that's really wonderful and you don't want to do Earth observation any other way, then you have to figure out a way to share with others and benefit in some way, and how that's going to happen. As the utopian view would be what Linear would say with sort of propagating the value back. Like you can compute the benefit information bits that were contributed by various actors, and then whatever money is made of it should propagate back all the way. If that actually worked, then everybody will like that. It would be against it. But how do we get there? It's a hard problem, but it only becomes even possible to discuss with everyone once you have that thing, not Caleb's demo, but what I'm trying to convince you that Caleb demo could look like if we did much more. So once it's there, then it's gonna be, well, why am I writing scripts and waiting when these people can just click a few things, and then if I clicked on a few things and I got this really great thing, but I only spent 15 minutes, I'll share it, at first. So that's sort of the answer to that question.
Thank you very much.
It's very good. This is a fantastic conversation. We should go on, but we are about 10 minutes over schedule. So I think let's thank the speaker one more time.
Thank you.
And I think now for the closing comments.
So, well, what a day. So we had very nice presentations today. I personally learned a lot today. Well, with this fantastic talk given by Nebojsa, our workshop also came to an end. So, well, this morning I said a lot of things about the workshop itself, but now I would like to take the opportunity and appreciate every and each of you for your participation. We had a successful event only because of you. Your dedication, your participation, your submission, your fantastic talks made this workshop a successful event, in my opinion. And I would like to take the opportunity to appreciate Alina, Alexandra, Miriam, Joe for taking care of all the technical things. It's really difficult to switch between physical presentations and online presentations in such a smooth way. Thank you very much for that. And I also want to appreciate our keynote speakers, Nebojsa and Vipin, who came here all the way from the US to give these fantastic talks. I would like to as a token of appreciation, I would like to give you some small gifts. Yeah? This is a part of the plan, no? These gifts are from IARAI to Nebojsa and Vipin.
Small token.
And well, I also wish to appreciate all other organizers from European Space Agency, from Maxar Technologies, from IARAI, from Linz University, from Griffith, from RIKEN, from University of Tokyo. What else? And many other participants. But last but not least, thank you very much to every and each of you for your participation. I really appreciate it.